So it is now time to act and to know how to develop a model. For this reason we cover now in this lecture methods for model development as far as we know them. There are far more methods we should consider, but we concentrate on some of them where we are sure that the model is built in such a way that it can be used within its function in the given scenario and properly applied. In the third part of the series of lectures, we started with activities to model. We will continue now with methods for model development. Next we will have methods for model utilization. Then we go to look whether we can handle it automatically. We consider somehow evaluation of models, and finally we consider engineering, proper engineering of models and of model usage. So far we have been handling the model notion in the first 5 lectures in detail, and in the second part of the lecture we handled elements of models, components of models, especially the deep model inside a model, model suites, and of course also conceptual models. This time we want to go for modeling in the sense of to develop a model. That means in the sense of to develop or to act as for model development. This time we consider the first part of activities of to model. I remember that we considered in the MMM framework models, to model, and modeling. This MMM framework corresponds to the German language treatment. We have models, we have modellieren, and we have Modellierung as 3 different sides of the model. Now we handle here modellieren as the acts to model and the acts to use a model. In this lecture we look for appropriate methods for construction of a model according to the function of the model and depending on the task and on the properties we are targeting, of course within the setting of the model. This requires a bit of workmanship. For this reason we need to have methods that we can handle properly. This requires also some kind of support for reasoning and of course for preparation of models so that it can be properly used in the utilization scenario within the set of functions we want to support with the model in these utilization scenarios. As already said, to model is an activity consisting essentially of 2 parts. One part is model development based on activities, what we will handle in this chapter. And the second part is model deployment based on the activities of applying the model that we will handle in the next lecture. This lecture, for this reason, gives some insight on abstraction, on construction, composition, definition, integration, specification, invention, enrichment, adaptation, mutation, recombination, refinement, site use, and preparation for deployment. And of course how a theory can be developed to support all these acts and activities for model development. The next lecture we will explain how it can be done in a proper form for model usage. First of all, let's remember the stages of the model. In this lecture we consider mainly only greenfield development as the main issue. We do not really want to consider brownfield development for integration, adaptation, for evolution, modernization, for revision and migration. That is a specific lecture that will be given at a later stage in part 4. Typically, models are not really developed from scratch, but it is better to consider modeling from scratch first and then look how these greenfield development methods can be extended and refined to support also brownfield development. The stages of the model we consider here are first model development, with a description of the model, with the formulation of the model, with ramification and validation. The next lecture will be then model deployment, with elementary deployment, with paradigmatic deployment, with added value increase. And finally, we should also consider the deep model and the matrix synthesis, or the matrix injection into the model. The description consists of some kind of methods for exploration and of course also for model amalgamation. This time we therefore go for methods for model development and for a large variety of methods we can use. We have a number of methods we can use. We know in engineering collection methods, planning methods, intuitive methods, discursive methods, and calculation methods. The most of our modeling acts are concerned with collection methods. That means we know how to develop, maybe based on targeted questions, methods for order, and so on. Planning methods are providing some means for the methodology of negotiation, for new conception, for meiotics. I will come back to this Socratian method a little bit later. To have also intuitive methods, discursive methods, and calculation methods, and any other creativity technique. Methods can be also given in a rule-based setting. Then in this case we can go for method matrices, methods catalogs. They can also be given based on frameworks, especially for oriented on practical utilization. They can be also include specific techniques such as association techniques, map techniques, visualization techniques we already covered partially. They of course are based on a methodological frame, and of course we have to know the restrictions, how to apply and how not to apply the given method. That is a little glimpse on methods how to develop a model. Let's now go for the model development stories. That is a bit funny, but we can use our storyboard facilities for the somehow description of the development stories. That means with specific development scenes we can somehow try to develop a model. What it means? It means if we go now for a design science setting, we have a relevance stage, we have a modeling stage, we have later maybe a rigor stage, we have additionally a realization stage. Then we consider first of all the world of applications, next the world of our models, and finally the result of our modeling approach. That means in this case we start with the derivation of application domain goals and objectives, with the elicitation of application domain entities, with the derivation of application domain properties, with selection of quality criteria. Then we can evaluate them, then we can derive specific properties, or we can start with deriving modeling objectives and development of model acts, and then especially applying them, and then deriving again model properties. That means in this case we have a world of applications, somehow broken cycle, but a cycle that supports modeling. We have the modeling stage cycle in the world of models, And we have finally, after evaluating and after having reached a good quality of the model, we can now use the model for deriving the objectives of the, let's say, realization, and then for development of an implementation, as we do in computer science typically. The same is also valid for other known mediating modeling stories. If we go now for this kind of frameworks, then we have first the relevance stage, we have the modeling stage, we have the realization stage. This requires a specific reasoning on description, reasoning on prescription, reasoning on specification, and reasoning on coding. That means we are reasoning about the ways of operating in the application domain, about properties that are of relevance for the problem as that we target with the model, for reasoning about objectives that must be satisfied by the model, reasoning about the model architecture, the model properties, the model composition and the model elements, reasoning about properties of the model and satisfaction of the model objectives, reasoning about the targets and realization objectives, maybe if we want to have a model used for coding, then of course coding oriented reasoning, and finally of course assessment and some kind of guarantee specification based on corresponding reasoning methods. In this case, for system construction, we have a little somehow a rough story. First we handle application domain workflows, next we have workflows for modeling activities, then we have workflows for implementation of sub workflows, and of course also workflows for model evaluation sub activities. We can break these specific story parts into smaller stories, and then we have, for instance, for the sub workflow during modeling activities, first of all maybe some mapping, next we have some modeling activities to derive relevant concepts to be used in the model, we derive model properties, and then we can try to evaluate the corresponding model. That is a modeling story in general. If we go for conceptualization, we have a little bit simpler story. We go, of course, with concept development. Then we can somehow try to differentiate the requests. We can try to explain and to understand what has been done, to evaluate and to select, to develop concepts, to justify the concepts, to test, to evaluate, or maybe in general setting to experiment with the context and concepts. And then we can apply the concept within the model. That means in this case we enhance now for conceptualization the general system construction story with an conceptualization sub-story. Of course we have to consider some kind of quality regulations. For this reason we might be able to use the SPICE framework developed for software process improvement and proper engineering of software. We shall come back in the engineering part to this property again. SPICE has been basing on process dimensions that are somehow supporting capability dimensions, and for this reason we have process groups, processes, base practices, some kind of output work and some kind of input work. We can also use the corresponding capability levels, and we have in modeling almost the same way, except that we don't consider what is the quality of our origin that we are modeling. We can also use some kind of stereotyped model workflow, of course based on what has been reached so far. That means we start with some kind of solicitation or construction, with some kind of continue with some kind of exploration of subsidiary models, with some evaluation, with the formulation of the new model following the modeling schema, deployment, and finally maybe synthesis and integration of what has been achieved so far. That means we construct the corresponding model so that it functions properly in our utilization scenario. We can now map this kind of stereotype development and our workflows to some model cycles if we start from scratch. We start with exploration, continue with model construction, and finally with some kind of formal model formulation, and then we might use this model in such a way that we can be sure that it functions properly. Exploration means we start with maybe domain situation and perception models, or in general with some origins that are going to be disassembled, that are going to be becoming more matured. That means we start with demonstration and manifestation, and we develop maybe some nominal models. Then we use these nominal models for model amalgamation, for plausible model composition. Maybe we can add some steps for investigative design, and finally we have a result I would call real model. Now we can use the real model to develop a formal model, since we want to guarantee properties. We are not interested here in models that are somehow given and somehow maybe valid and somehow not valid. We want to have a facility to handle it formally. For this reason, we formulate a formal model based on investigation and initial formulation, based on a rational model extrapolation, based on assessment for elementary deployment. All this is based on some kind of modeling experience and modeling experience knowledge that has been developed. Of course, followed by different representations. This is now the part about the story. What about if we go now in an agile, experience-backed methodology way? So in this case, our second step and our first step can be somehow integrated. Then we reuse what we have gained so far. In this case, we explicate our experience, we elaborate whether it is sufficient, we look whether the purpose is properly supported, and then we can develop an somehow stereotyped model that is based on generic models. That means on our experience we have gained so far, and then we can add maybe some, even as an optional feature, mathematical model formulation. I repeat here that this is pretty similar to the mathematical method as a mold. We have problem consideration, domain situation models, we have formal mathematical model, we solve the task, we verify what we have been obtaining so far, we have some dependability results, and finally we might have some chance to use it in a proper form for the solution of the problem. We can also use some scenario stereotypes. For instance, if we are interested in the first aspect of models, that means in perception and utilization, then we can have steps in our scenario to know, to understand, to be able to apply, to practice, to analyze, to design, to organize and to synthesize, and finally to evaluate and to appreciate. This is nothing else as the maturity levels of perception and utilization we have been considering for the functions of the models. In this case, we support the model as an instrument based on the orientation, based on communication and the information provided, based on a proper representation of the situation, using some visualization, and maybe using some kind of representation facilities like diagrams. We can also have here alternative steps. For instance, instead of understand, we can use the model as an inspiring facility. That is often done in the UML business. Instead of to be able to apply, we should be able to be supported, to guided, to instructed. Instead of practicing and carrying on, we can use, then we can manage to use, and then we can reorganize, and then we can refine our model. In this case, we have some kind of modeling cycles. That is a modeling cycle that we have been using in our schema before in the modeling stage. In this case, in the modeling stage, we said, okay, fine, we have some kind of recapitulation, some kind of derivation, some kind of development, and some kind of evaluation. That means in this case we can now use what we have been doing so far as a cycle of modeling. That means in this case we have maybe even multi-iterative cycles going several times through it. And we have maybe all other development and utilization models we can use. For instance, Poya's approach to mathematical modeling and problem solution. We can add agile and explorative modeling to these modeling cycles. We can, of course, also somehow avoid the advanced waterfall model or meta model for model development, using some other approaches, maybe based on the classical way how we consider agile modeling, especially in the case if already something has been developed as an alternative approach here where we use our experience. Okay, let's now handle the modeling acts in detail. Of course, concentrating only on greenfield development. It will be similar for brownfield development, but this will be delayed to a later stage. Remember, we have had the modeling act. The modeling act is nothing else as a generalization of the classical speech act. That means in this case we select what we want to have, we do what we want to have and perform properly. We might reason on that, and then we might prepare the model in a proper way. Okay, the first step in our stage would be exploration. We start with a well-defined modeling task, with a well-defined scope and consider choices. Maybe we use some kind of deductive approaches or inductive approaches or mixed approaches, whatever can be used in this case. We disassemble what we know from our origin. We try to manifest what we have been observing. That means it is some kind of monstration. And finally we use some perception or nominal models to get a rough subsidiary model based on a glossary, and of course in this case we can have at least a glimpse of what we want to have. All this is based on the task and the function a model should have within our utilization scenarios. Okay, disassembling means in this case imagination and exploration, somehow focusing in a proper form and restricting our attention, and somehow use our thoughts already for thinking about future evolution. In this case we could consider also artifacts and variants depending on the given utilization scenario and its variants. For instance, if we use a description-prescription scenario, We could look what kind of reality we want really to represent, what kind of augmentation we want to have in future for our systems and our environments, what kind of versions we should consider. I mean, in this case, disassembling means nothing else as having a corresponding way to decompose the origin in such a way that we can handle it by a model. The next step will be monstration and, of course, the derivation of a nominal and perception model. Before that, let's look a little bit more into details into disassembler. First of all, we should somehow try to decompose a model and the origin in a proper form. And of course, in this case, the model being in a proper form. We start with dissolution. We can use segmentation methods. We can use analysis methods for maintaining coherence, especially if we are using a model suite. We can start with abstract refinement and categorization, and with the corresponding examination of facilities. Monstration and manifestation is our way to construct, to form the model. I would say to preform the model. And we can use the classical Galilean thought experiments for augmentation. Of course, and in this case we base it on life situations and maybe on what has been observed, whatever has been observed for our origins. That means we are making our modeling task and our modeling problem transparent. Okay, then we can handle restrictions. Then we can also look for obtaining the most simple models. That means in this case we look, because of we want to support parsimony, for something like Occam's razor principles or for Solomonoff principles. Then we start to consider main features and elements of models, and of course we can now use our W star H framework to represent whatever has been developed. Monstration includes also our situation model consideration, or the main situation model. It is a little bit different from demonstration. Monstration is the act of demonstrating and of exhibiting, of proving, especially the proof beyond the possibility of, let's say, our depth, and of course based on evidence and based on what we have, at least in our hands, for reasoning. Demonstration is something different. That means in this case we could consider familiar situations and examples that would allow us to use our experience, how we do in brownfield development, consideration of alterations of the situation and exploration of the space of opportunities, and constructing the corresponding domain situation or situation model. In this case we come down directly with a glossary and the first maybe common domain situation models that we could use for further model development. In this case we could also consider variants of structures and behavior. We could also produce a corresponding domain situation or situation model in general. And in this case we bring into existence already a pre-model and parts and elements of our model, so that we can construct it in a proper form. We consider and reflect what we want to have, and of course in this case we have to negotiate with our stakeholders, with our community of practice, that the model is really properly going to be developed. Then we can have a number of variables to consider, especially variables for our perception models and or maybe for our nominational models. The nominal models include, of course, something like a proper language selection, a proper theoretical background selection, a background settlement that comes together with a deep model. Maybe it's coming already together with the origin, but it will be a part of the deep model. Then we can go for composition, to have a generic structure, to have a particular structure, and finally we have a model that is a generalization of a subsidiary model. Think about how people in physics are developing models. They say, okay, fine, we take this component, throw away the other component, take a third component, and handle or bundle the components we would like to have together by, let's say, some additive framework. That means in this case we have a number of variables we can use as we use in inverse modeling. Okay, in this case we have some kind of agreement on the function a model should have and support, on hypotheses and statements. We can have a proper negotiation and refinement, especially if we look later on the quality of a model or quality characteristics of a model, based maybe on some SWOT framework for capacity and potential somehow evaluation. We have an explicit statement about evolution. I was putting here the last point, especially because of often we forget about the evolution of a model that will be completely different from what we have so far. Okay, finally we can explicate the nominal and perception models based on the background and the context of our community of practice, with a basic exploration and with an explication of the grounding. Again, we base anything on a proper agreement on the background, that means in a proper deep model. And for this reason we should somehow be able to evaluate potential and capacity of our models. Okay, the second set of steps considers amalgamation. Amalgamation of good and of bad features. That is a proper combination of elements of models in such a way that these elements somehow are coherent. For this reason we use some kind of, let's say, amalgamation method in order to compose a proper model out of the components. That means we have to have a plausible model composition. We might use what people are using in forensics, investigative design, and finally we design some candidate for a real model. In this case we use this amalgamation as some kind of model transformation method in such a way that the real model is properly designed. Amalgamation can be based on inductive reasoning. Inductive reasoning starts with some knowledge, with some models we have, with some data, and our model and our knowledge does not somehow allow us to derive our data. Since we aim at discovering a formula that is not uniquely defined, that is coherent with our knowledge, our models and our data, and that allows us to explain the data we have in mind. That means in this case we have nothing else as we try to derive some kind of alpha, so that alpha does not somehow be not coherent or maybe conflict with our data, our model and our knowledge, but at the same time alpha explains our data. That means in this case we use this kind of inductive reasoning method, sample by sample, data by data, in order to explain what we need to have. That is nothing else as maybe induction. Additionally, we can have also adduction. Okay, then we have, for instance, for database models, a number of strategies for control of development. We have top-down strategies, we have bottom-up strategies, we have mixed, we have inside-out and modular techniques. We can also use AI approaches. Top-down starts from top, from the center, from the most, let's say, general element, and decomposes it so that we have a way how to express our elements of the model in a proper form. Bottom-up starts in a different way. Bottom-up is a construction way that we start with us in database development with basic attributes that could also be, of course, complex, but with basic attributes, and compose the corresponding database types based on some kind of combination of these attributes. The mixed and hybrid approach is a combination of top-down and bottom-up operations using these methods in an iterative way. We have to start with a skeleton and maybe with a list of obligations, and we use it for derivation of our model. The inside-out method is nothing else as we develop first the most important, the central elements, and then we proceed further to closed elements, maybe based on a neighborhood function, so that we have finally maybe the model developed with the basic and central elements first. Modular approaches start typically with the development of an architecture or a skeleton of the model that should be developed, and then we use this modularity to develop those components that are necessary, that are somehow combinable through this skeleton, so then we can have a model that has at least already an inner structure. AI methods are mainly those methods we are using for searching, depth first search, breadth first search, hill climbing, and beam or best first or branch and bound techniques, or dynamic programming, A star, AO star, heuristic methods, and anything what else we can have here for the composition of database models. In this case, we can have some kind of guideline, that is a general workflow for modeling, and some kind of micro steps that we can use in modeling, at least for the first two phases. We use in this case a number of operations. A typical is, for instance, decompose something into different parts. We can also use something like decompose entity or relationship types in a proper way. We can also decompose components of an entity type to become somehow associated with that central part of the entity type. We can also decompose type in such ways that we have maybe a relationship type between entity types, or that we have some kind of hierarchy inside that. This is all local top-down operations. We can have also somehow local bottom-up operations. In the case of local top-down methods, we are using nothing else as a classical graph grammar. We have in this case, in the graph grammar, some kind of components that can be decomposed, and then we have something like a gluing submodel that glues our parts that we are decomposing with the environment of the given type. In this case, we can say, okay, fine, let's now glue, or let's now decompose, let's say, an entity type L1 with some glues with K1 and K2 into an entity type R1 and R2 that is again somehow connected through a relationship type R3, and we have of course to maintain the context of the type. And in this case we say, okay, fine, the rule says the first context goes with R1, the second context goes with R2. So in this case we do not lose elements of our model, of our database schema, while we are decomposing a type into two different types. This is one of the operations. The graph grammar approach is a pretty general one. It allows us to decompose these types in a proper form so that we have now rules that we can apply whenever we want to have a certain way of decomposing in a top-down approach our database schema that has been so far developed. Okay, for model amalgamation we start with maybe a plausible model composition. Of course, we develop, in this case, strategies and tactics for model composition first, or we apply them at least when we have it already in our vocabulary and our approaches. We unify, we consolidate, we have some ways to formulate in an explicit form the criteria for adequacy and dependability. We have an empiric evaluation and validation of the situation model or the domain situation model, and we can check for plausibility and check against the goals and purposes. Yeah, for database models it is a little bit more sophisticated. We can agree maybe on a global as design strategy, and in this case we say, okay, fine, our local models can be somehow derived. In this case we try, of course, to use now some kind of unification of viewpoints because of we have to derive the local models in a proper form based on the global schema. Then we can look for explicit realizability, for proper adequacy and dependability, for an empiric evaluation. In this case we would like to have maybe some homomorphic mapping of origins, of elements of origins to the given model. We have a number of typical parameters we can apply for this global as design framework as we have been doing it for the higher order entity relationship model in the past. And of course we say, okay, fine, we try to satisfy the goals and the purposes and the functions based on the style of the database model that should be developed. That of course includes the database schema and the derived viewpoints as view schemata based on the global schema. Okay, the second step in model amalgamation will be some kind of investigative design. In this case we try to reconsider whatever has been developed. That means we negotiate and exposit what has been developed. We experiment with alternative. We check against the grounding and the basis so that we have a proper support for the grounding and the basis, and so for this reason a proper support for the deep model. We develop design alternative, prioritize them. We develop maybe practical guidelines and maybe at least constraints for rationality, and we investigate whether we achieve in this way our goal of the model. So in this case a real model design would be based on some kind of idealization. That is one of the phenomena properties we considered already in the first part, or an extension or distortion. We clarify essential, typical, relevant aspects and forget about the others. We put our emphasis on the purpose and the added value of the model in the given application, in the given application scenario, so that the model functions in a proper way. We follow the basic principles of well-formatedness, and of course we hope that we can somehow have a proper support for analogy. That means the structures might correspond to a natural situation, to the given origins, or to our thoughts we have, let's say, developed in order to realize a system or something like that. And of course it should be clear, simple, straightforward. The real model design for conceptual database schema includes, for this reason, that we aim at a fully defined real model, a well understood primary application portfolio. We know the constraints in an explicit or maybe in an implicit but default based form. We use explicit concepts that are coming for conceptual database schemata from the namespace and from the concept space. Therefore, we can use the glossary directly, and we have a number of optional facilities, like something like different definitional frames and maybe some specific means for constructing a database structure. And in this case, maybe we have to consider also a model suite instead of a singleton real model. So the third step will be now model formulation. And model formulation in this case as a formal model. We start with perception models. We have a comprehensive, exhaustive and formal model in mind. For this reason we have a mini step of investigation and initial formal model formulation, formal model extrapolation and reconsideration, so that we can be sure that the model is really behaving properly in our given scenario where it is used. We can assess by elementary deployment. We can also use model evaluation and assessment procedures. The last two parts I will handle a little bit later in the next lectures. Okay, in this case a formal model formulation would somehow support us to solve some of the problems. Idealization and extension, and proper establishment of the focus, an explicit formulation of the grounding and the basis, so that we know our deep model that can be somehow derived from the grounding and basis, together with the methods that are already given by the matrix of our development method. We can somehow describe in an explicit form the adequacy, the justification and the quality criteria. We have appropriate methods for the purpose. We have methods that support the utilization, and we have maybe a negotiation phase. At least for database development we use it quite heavily. And of course we have some kind of reduction to naive aspects. Okay, the first mini step would be investigation and initial formal model formulation. We can somehow try to formulate the real model with an appropriate depiction, explicit profile and portfolio with artifacts. At least the artifact world should be represented in our model in a proper form, or at least the origins world, representing the context, the roles and the obligations given by the community of practice. Then we have maybe some way to formulate the adequacy and dependability in a proper way, and some way to reason about the background. And in this case we might enhance our model to a model suite that at least uses also some kind of representation model. For instance, in database modeling we say, okay, fine, we have something like a formal model, and we have some kind of diagram model as a representation of the formal model. Typically we forget about the formal model behind and use only the representation model, with the hope that the formal model can be somehow derived from the given diagrammatic model. In this case we use an argument calculus. We have arguments that provide some kind of reason why we have been doing it in this way. That means in this case we can have premises, we can have methods of reasoning or methods of deduction, and of course we should also be able to make a conclusion. That is the same as we use with the classical argument calculus. It is of course based on the grounds of our knowledge, And we have a number of components of arguments. An argument can be structured in making a claim, having the data, having a warrant, using some kind of backing, maybe having some kind of rebuttal subphase, and some kind of qualifier as a quality criteria for the goal we wanted to achieve. This can be based on argument logics. See Gabriel Bernhard for base reasoning. See Simari for general argument calculi, or in general maybe Rasher. We have in this case some kind of categorical assertions. If you use some cautious assertions, and can somehow derive provisute assertions. There's a mistake here. In this case, you have a disputation as a dialogue, and you can in this case derive the corresponding argument calculus. It should not be done in this formal way, but it can be supported by this formal way. Additionally, we use abduction. Abduction is nothing else as reasoning on the causes for something. So it means we have a number of data or data collection, and we try to have an explanation of the data in such a way that this explanation is as minimal as possible. In this case we can say, okay, fine, based on the premises, then our hypothesis is probably true. This can be properly applied to model development. Again, the claim is we have not to do it in this formal logical way, but this formal logical way can support our reasoning. The next step will be the formal model extrapolation. So far the model is incomplete and not yet really properly settled and not yet properly supporting the functions. It might not yet be adequate and dependable. For this reason, we want now to have some kind of completion of the model in such a way that the model is adequate and dependable and functions pretty well in our utilization scenario. So in this case we can say, okay, fine, we can have some insight into the application domain requirements. We should understand our background already quite well, and for this reason we can use it in the proper form. And then we have some model construction requirements, and we have some generic models maybe behind our development. Then we can reconsider the formal model, maybe playing with different variations, independence or dependence directions, phenotype versus genotype representation. That means we use a proper granularity for our model. We can add auxiliary elements. We can explicate the general structure or architecture, and of course also the dynamics that is supported by the model. We can have variants of structures and dynamics, and we have potential revision of the background. And then in this case we have maybe a number of hidden and invisible parameters, especially those that go together with a deep model at a later stage. For a conceptual model or conceptual database model, we can look for the best fitted hierarchy structure. We can look for real and fictitious cycles. We can look for adhesion and cohesion of types, so that we can separate the types in the proper form. We can look for some kind of modularization based on components and connections, maybe harnesses. And then in this case we can have a proper selection of the element kind, weakening of the global as design approach. We can use a schema skeleton and a schema architecture. We can use some kind of cognition completeness, so that all elements that we can have in our perception models are properly represented. And we can have some kind of skeleton abstraction for the generic model. In this case, we use some kind of assessment procedure by elementary deployment. We have methods for assessment against the real, let's say, not the real world, but what we observe, our empirical world. We can now assess corroboration. We can now test and experiment in a proper form within our, let's say, utilization scenarios and use spectra where the model should function. And we can evaluate the capacity and potential as a given inside property of a given model. And we can validate with situation, perception and the real models in such a way that we are sure that we are representing the right part of our origin in a proper form. And then we can look whether it is deployable in a proper form. That means in this case we have a number of stages. The state of the art is, of course, that not all stages are properly supported so far in all kinds of computer science modeling activities, but they can be somehow enhanced. In general, we have nothing else as inferring, preserving, modifying, and replacing procedures that are supporting our modeling in computer science. And then we can look for assessment. And the assessment would be nothing else as assessing the model against the potential deployment. Of course, in this case, maybe by elementary deployment. Elementary deployment means nothing else as we are considering the most essential elementary cases and the most difficult boundary cases. So in this case we validate with our origin, our domain situation or situation in general, with our perception real models. In this case we can associate the model to the patterns of those, let's say, real perception or situation models we are using. We can understand the assumptions that go behind. And for this reason we have now a very good way how to assess the potential and capacity of our model. We can develop a number of semiotic rules, classify the conceptions. Maybe we have also some kind of specific ways to support the communication within the community of practice. We can use some kind of representation means that are really proper. We can understand what is the semiotics behind. We can coordinate in a proper form, evaluate, and of course derive also invariance properties, especially the purpose and the function should be invariant for the origin and the model, at least restricted to the given utilization scenario. We can try to articulate the facets and modify and replace or preserve or infer the conceptions we need to have. That would be the same case as we have with database modeling. We can now look for elementary utilization and deployment in such a way that we are sure that this model functions properly. That means we are evaluating our model in a proper form, so that it is going to function properly. So in this case we look for justification. We have a number of calculi we could use in this case for rational evaluation and for empirical evaluation in the given scenario, in a given way. And we can use this kind of justification in order to revise or potentially revise our model in such a way that it is properly functioning in the given scenario. And in this case we can combine the results of the model evaluation, and in this case we have of course a proper statement on dependability of the model by empirical explanatory statements, by statements about rational coherence, by statements about validation and maybe also falsification, and by being sure that this model is stable and has a proper plasticity. That means in this case we have now we can be now sure that our model is a proper model and it functions properly in our utilization scenarios. And then in this case we can say, okay, fine, we can now look whether the model composition was a proper one. Again, we can use the same framework as we have been using for concept development. We say, okay, fine, which elements of the model are really typical, which are relevant, which are important, and we can use now a number of construction expressions in order to handle the model composition. That means it would give us a way to look what should be really done first and what could be delayed a bit or what should never be done. So this will lead us in our chapter 15 to model evaluation and assessment based on a number of methods. We have now in chapter 15 different maturity levels, different goals, purpose and functions to consider, general quality steps. We consider the capability and the capacity and the potential of our model, the added value of the model development itself can be also evaluated, and of course in this case we would have a quality assessment and a quality passport finally based on our assessment methods we have been using. I will not consider this in detail here. I will somehow delay it to chapter 15 of our lecture. That would mean that we have some kind of testing and assessment procedure. Testing and assessment can be done systematically by specifying first a test goal and a test plan. Then getting the right testers, of course within our community of practice, and the right experimenters. Then we can test the tasks and the methods, developing test scenarios, and finally we have some kind of performance measurement. That is a systematical testing that people in natural sciences, see for instance in chemistry, are using properly for assessing the quality. We can use it in the same way, and we will do it in section 15 or chapter 15. If we want to have some kind of more agile method, then we can say, okay, fine, the exploitation of experience is based on what we know so far. We elaborate the artifacts, the models, the origins that are of interest. We have maybe a better understanding of the purpose, of the background, and maybe of the context. And maybe we have other general models. We have already been considering generic models, and for this reason I can somehow restrict my attention here to a part of these steps. In this case we have a formal model formulation now based on the investigation and initial formal model formulation. We have a rational model extrapolation, and we have assessment reconsideration, especially whenever we want to be sure that the evolution can be somehow maintained by our model, the evolution of our, let's say, functions in somehow a number of utilization scenarios. And then we have also the model evaluation in a formal form. This corresponds again to the mathematical model formulation and utilization. We have been considering it several times already. That means in this case we are using the same way how mathematics is using model formulation and model utilization, based on the background, based on variation methods, based on some kind of analogical reasoning methods, based on a decomposition approach. That means in this case we start with top-down methods, based on somehow maybe principles like the superposition principles that supports nonlinear modeling in mathematics at least. Okay, composition methods, only very brief in a nutshell. We considered already a composition method that is based on stereotypes that can somehow be used for refining them to pattern based on some styles. We can use composers and we can derive finally templates, as we did already for our search models and our search approaches and our search support. In this case, we said, okay, fine, for eager data-oriented or lazy data-oriented or active coordinated search, we can use this kind of model composition. In the same way, we can handle also model composition in our modeling framework. Okay, that is now the way how to model properly. In the next lecture, I will handle model utilization, usage, deployment, revision, and of course also deep model synthesis. That means in this case we will develop now methods for model utilization in a proper form. In this case, what it means to have some kind of deployment for elementary and paradigms at least, what it means to have an instrument, what kind of scenarios we can have now for model utilization. I will apply it to service models and to model checking. We should also consider the rigor cycle and also other design science approaches. And of course we should also reconsider our deep model and the synthesis of the matrix of our model or model suites. This is now the promise for the next lecture. Here I can thank you for your attention. Thank you for your understanding, and I hope to see you very soon while we are going to act and to use a model in a proper form.